All right, so this is an extra calculus interlude. So there's a lot of things I think you have to be very careful about in calculus. And so, for instance, what's the derivative of x cubed, x to the 3/2, x to the root 2? So what are the answers? 3x squared.
Yeah, subtract fractions.
To the
1/2.
To the 1/2. And the other one?
2x.
Right. The proofs are all very different. For this, it's x plus h cubed minus x cubed over h. Take the limit as h goes to 0. This is the binomial theorem. X plus h cubed is x cubed plus 3x squared h plus dot dot dot. We can't use the binomial theorem for the derivative of x to the 3/2. So when you teach calculus, how do you teach the derivative? This is a point that I find is often glossed over.
Usually I do implicit is the approach that I was taught at least.
So is that if f of x is x to the 3/2, g of x, if you define that to be f of x squared, is x cubed.
Yeah.
Yep. So that's a great way to do it. And for that, you need to know the power rule or the chain rule. You could also do the following if you're brave. X plus h to the 3/2 minus x to the 3/2 over h, and then multiply by, what should I multiply by? By the conjugate. X plus h to the 3/2 plus x to the 3/2 over x plus h to the 3/2 plus x to the 3/2. And then you can ask, will that trick work for all fractional powers? Or is there something nice about 1/2? How do you do x to the root 2?
That one, I told them, well, that one isn't an optional project.
Right.
For logarithmic differentiation.
So you need to know that, x to the root 2 is e to the root 2 log x, and it's the chain rule. But it's not even clear initially, what does it mean to raise something to the root 2 power? I know what it means to square something. I can do x times x. I can even understand a square root. I'm looking for y such that y times y equals x. But to raise something to the root 2 power, we're really using e to the x is the sum of x to the n over n factorial. And now we've reduced everything to just working with nice powers. The other thing, just to briefly mention for the calculus interlude, is the sum rule. So the derivative of a sum is the sum of the derivatives, right? So if I give you 3 functions, f plus g plus h, normally I don't think this is proven carefully. What you really have to do is write this as f plus g plus h prime. And now we can use the sum rule because it's just 2 functions. And then this is a chance to use all those different rules. And now this is just f prime plus g prime plus h prime. So the question is, what if you have an infinite sum? So for example, if I consider the sum of sine n factorial x over 2 to the n, n goes from 0 to infinity. So we know the sine is at most 1 in absolute value, so it's going to converge. Because 2 to the n is growing sufficiently fast. What would you like to say the derivative of this sum is? If you had your wish, if calculus was nice, what should the derivative of this infinite sum be?
Sum of the derivatives.
Sum of the derivatives. So if that's the case, then you would have the sum, n goes from 0 to infinity, of n factorial cosine n factorial x over 2 to the n. At 0, at x equals 0, you get the sum, n goes from 0 to infinity, of n factorial over 2 to the n, which is infinity. So you cannot always take the derivative of an infinite sum. And then the last one is, you said you teach multi? Do you teach them that you can't always switch the order of integration?
Yes. Yeah.
Okay, and you have an example for that?
Oh, not off the top of my head. No.
Okay, so then this will be the last thing of the interlude is an example. So instead of doing a double integral, I'm going to do a double sum because that's just easier to do. So the sum over m of a m n is not always equal to the sum over m of a m n. And this is the best example I know. So we're going to consider an infinite lattice of pairs. I'll just do 2 more rows. So this is just a calculus interlude. So this is the pair 0, 0, 1, 0, 2, 0, dot, dot, dot. And I'm going to define my sequence as follows. It's +1, -1, and then 0, the rest of infinity. 0, +1, -1, and then 0 for all infinity. 0, 0, +1, -1, 0 for all infinity. If we do columns, then rows, what do we get? So what does each column sum to? So since each column sums to 0, and then we go across the rows, we get 0. If we do rows, then columns, what does each row sum to?
Well, the bottom one's 1.
The bottom one is 1, and then every other row sums to 0. And so if we do it in that way, we get 1. So here's an example where it matters which way you sum. And instead of using sequence, you can always smear this out and make this into functions.
Sure.
And the problem is whenever you have infinities in mathematics, you have to be careful. So this is just a really short calculus interlude of just why you have to be careful, why these things have to be proven, that sometimes we can't just switch things.
I mean, it was really nice when I taught linear algebra because you see the the dimensions of matrices not line up, and that was so much easier to show.
Yes. And so this is, to me, I always want to have a physical example. You should always, one of my professors at Yale, Peter Jones, said, if you remove a condition, the proof should either be a lot harder or you should come up with a counterexample. And so for a lot of these sums, we need the sum of the absolute value is finite, then we can switch. The integral of the absolute is finite, then we can switch. Okay, so I promised to do some applications to chemistry. And given that I was not given much notice about this, some of this will be made up on the spot, so I encourage you to bear with me. The application will come. So I am old, I am distinguished, I have a huge amount of accomplishments. Henry did not have time to get into everything. One of the ones I am proudest of is I am undefeated at tic-tac-toe at the local elementary school. No kid has ever defeated me. I've been tied, but no kid has ever, and I do have some victories to my. So I will share with you, and I know this is being recorded, my tic-tac-toe sequence. So how many opening moves are there in tic-tac-toe? 9. How many responses? So that means after everybody moves, that's 72 possible game states to be aware of. That's a lot. And it just gets worse as you keep going further and further down. Let's look at this again. Up to symmetry, how many opening moves are there in tic-tac-toe?
9.
There's 9 moves, but I claim some of the moves are equivalent. Why 4?
Because if you flip the board, it's really the same move. Like if you go in the corner, it's the same as going in that corner.
Okay, so the corners are all one type of move. What else is an equivalent move?
In between the corners.
So the middles would be another type of move. And what else?
Oh, the center, that's only 3.
So there's really only 3 opening moves in tic-tac-toe up to symmetry. Does it matter which corner you go to? I can rotate. Now you can start to analyze how many responses are there. So what we have to do is we have to break it up into 3 cases. And this is a great way to talk about how mathematicians think. I would much rather do a lot of easy problems than one hard problem. Let's just break things up into cases. So X goes there, X goes here, X goes here. Which case do you think is going to be the easiest to analyze? Corner, middle, center.
Corner, I guess, because there's 4.
The middle, because there's only that one.
So in the middle, how many distinct responses up to symmetry are there? 2. So if I go here, somebody can go either in the corner or they can go in the middle. So there's only 2 responses here. If I go in the top middle, which squares are the same as others? Are all the corners equal to each other? Right, so the top 2 are the same. Now, can I get to the top left and the top right by rotating? Can I, if I have X and O like this, can I get from one to another just by rotating? I have to flip. So I can get from one to the other by flipping. Is that okay? Do you want to count OX in the top row as different than blank XO? Or for the purposes of analyzing, do you want them to be considered the same? Right, what is the goal? To win, to analyze the game. I don't care if I'm looking at the game or the mirror image of a game. And so this is a great way to talk about notation, canonical form. How do I want to present things? That if I only care about analyzing who wins, then the 2 moves over there are equivalent. And this is now the link to chemistry, is that you can have compounds that are mirror images of each other. And when you start to look at how many ways can you combine the different atoms to make molecules, I hope I'm using the right language, it's been so long.
Doing great.
All right, excellent. You have lots of ways of combining them. And some of them might be equivalent under rotation. Well, if they're equivalent under rotation, that's the same. What if they're equivalent under flipping? Is that the same chemically? And the answer is no. So you can have 2 compounds that have essentially the same structure, but they're mirror images of each other, and they will have very different behavior. And so this is a great way to then ask, how many different compounds can I create up to symmetry? And which symmetries do I consider important? For tic-tac-toe, I do not distinguish between a game and its mirror image. And this is where I teach a class on the mathematics of Lego. When we have an equipment malfunction, I will tell you how the class came to be. And I talk about a very famous problem. If you have 6 2x4 Lego bricks, how many ways can you combine them? This is not a well-posed question. So in your mind, what do you think of when I ask how many ways can you combine 6 2x4 Lego bricks? How am I allowed to combine them? So I see somebody go, I must stack them. So do you have to have something of height 6? Could you go to height 4 and then go back down? Maybe. Do they all have to be connected to each other? Could you have 2 different things, something of height 2 and something of height 4, and they're just disjoined? If you allow yourself to put a piece down in the upper right corner and pivot it, you actually get this infinitely many possibilities, depending on the angle you use. So you might say, in order to make this problem well defined, I will only place things at right angles. I'm trying to think if I've seen a Lego set with a rectangular brick going into a rectangular brick, not at a right angle.
They have ones now that have.
They have special pieces that have angles, but I'm saying, I don't think I've seen a rectangular piece going into another rectangular piece at a non-right. I mean, I would do this all the time when I would build things, but I don't recall any Lego set doing that they always have rectangular piece into rectangular piece in a right angle. And then it becomes an interesting question, can you count how many ways there are to do this? It is a very challenging question. And there's a lot of, good, and if anybody's interested, I can share with you some really hard papers that go through this and deal with symmetries and whatnot. All right, getting back to the game at hand, if we move in the middle, the two corners up top are different than the two corners down below. Oops. Okay. What's next that's equivalent? The two sides are equivalent under flipping. And then you can do like the center and the bottom. So there's 5 possibilities here. If we go in the upper left corner, how many ways are there? So what moves are equivalent? Good. The two middles that touch the X are equivalent. Yep. And then the two corners would be equivalent. And then the middle. And see how I'm going very methodically like this. I think this is a better way to go through things than the other one. And so I would actually say, let's go back here and let's change the ordering just to make it less likely that we're going to forget something. And it's good to talk about methodical ways to go through. I'll make these the 2, 3 move, the 4 move, the 5 move. And we see if we do it like this, there's only 12 possibilities, which is much less than 72. So if I'm trying to analyze tic-tac-toe, there's really only 12 game states after the first pair of moves. When I'm playing kids, what do you think my goal is? As a rule of thumb, yes. And I'm hoping the audio did not hear that. When I'm playing, what do you think my objective is when I'm playing an elementary school kid? I'm sorry, having them think, absolutely strategize, yes. Well, do you think my goal is to win?
Help them figure out how they would, could win.
My goal is not to win. My goal is not to lose.
Right.
And so when my son and I would play chess, my goal was not to lose to him. And his goal was not to lose to me. So we would both be very happy with a stalemate because then neither one of us lost. And so sometimes, in order to go for the win, you have to expose yourself. And so if I'm playing tic-tac-toe, normally they have me as the second person. My strategy will be to play it safe, to go for the tie. So it's just worth analyzing things a little bit. So where do you think the most common opening move is? Middle. So we said that I only have 2 responses. So let's analyze one response when I go in one of the middles, and I'll go over there. And I know we're doing chemistry, this is not oxygen. So now all I have to do is analyze what could happen. How many responses does the first person have to this? So what are the possibilities? So where can X, how many distinct places can X go?
Literally, there's 7.
There's literally 7. Can we narrow it down from 7 a little bit? 4. You could go in the corners above or below the O, the middles above or below the X, the corners away from the O. So there's only 4 possibilities. I'm going to assume X is playing to win. And so if we start looking at things, we can start looking at, analyzing the game states. So if X goes here on its first move and I respond here, let's look and see what happens if X goes here. What do I have to do? I have to go down to the bottom corner.
X wins.
X wins. Where can X go to win? Upper left? Any other place X can win? Top middle. X has 2 ways to win, at a minimum, maybe more. But we know X has at least 2 ways to win. So we know if I go in the middle, we know I'm going to lose. If I'm playing against a good opponent.
Wait, you're O or you're O?
I'm O. So if X goes in the middle and if X goes in the center and I go in the middle, a good X will beat me. And so then the question becomes, okay, I know I can't go there. So now I know that if X goes in the center, my only response has to be to go in the corner. And then you can start to analyze. So how many places can X go now? What are the possibilities? Describe them geometrically. So what's one of the places? Middle. So, oops. So there's the two middles, the two outside corners.
So you're saying if the top right game that we were just doing,
Yes,
if you're against someone, they go first, they go middle, you don't wanna go middle right?
correct. You don't want to go in
Because
any of the
in that
middles,
situation-
right? Because if you go middle to center, a good opponent will always beat you.
Gotcha, okay.
And so what I'm trying to do here is trying to talk about the thought process. How do you analyze a complicated problem? You break it up into smaller, more manageable pieces. And the harder the problem is, the more pieces you break it up. Now I've broken up, there are two cases if you go in the middle. If you go in the center, sorry, if you go in the center, I either go in the middle or I go in a corner. We just showed that if I go in the middle, I can lose, so I have to go in a corner. Now the question is, can player one beat me if I go in the corner? And now there's 4 cases to consider, and then there's my responses to those. One of the things that's simplified is I know that if there's ever 2 X's in a row and I don't block it, then on the next turn I'm going to lose. So this trims the game tree down. So again, I'm not going to go through all the analysis here. You can show that if you play properly, you can force a draw in this configuration. Okay? So, and then you have to analyze the other 2 cases where if the first person goes, they don't go in the center, which is actually not a bad strategy. Because most people are used to responding to the center. So if you don't go in the center, you put somebody in a little bit of an uncomfort zone. Do you think it's bad to go first in tic-tac-toe? Can it hurt you to go first? Why not?
Because if you go first, they have less responses that they can do, and also, I mean, if you go first, the worst thing you can do is draw.
But why?
But why? Because if you control, like in that X there, either I win because you went in the middle, or I stay only because you went in the corner.
What's the goal in tic-tac-toe?
Not to lose.
Not to lose or to win. But so, in some sense, if you go first, you're just giving yourself an extra X on the board and then passing it off to player 2 and saying, player 2, I'm going to let you go first. But you can't use this square, which I'm already putting for myself. It can't hurt me to go first in tic-tac-toe. It may not help, but it can't hurt. In chess has not been analyzed. It might be bad to actually go first. There are certain games where whoever moves first puts themselves into a bad position that the other person can exploit. Okay, nobody got Wrath of Khan. Has anybody seen Star Trek Next Generation? Excellent, okay. So there's one episode where Data is an android, and he is playing a game against a race that's known for their strategic insight. And he loses, and he can't believe that he lost, and his crewmates can't believe that he lost. He should be able to outcompute the person. And eventually what he realized is whoever moves first loses. Whoever tries to go on the offense loses. The only viable strategy is to play defensively. If the other person wants to attack, they will expose themselves and you can take advantage of that. If you play defensively, you can maintain that position indefinitely. And so for a lot of these games, the analysis can become very tricky, but you want to try to break it up into small, manageable parts. Everybody's seen tic-tac-toe. This is a game that I think even kindergartners are familiar with. Do we all agree that the game is boring? So we want to make the game interesting. So there's lots of ways to make tic-tac-toe interesting. Does anybody know any interesting versions of tic-tac-toe?
My 4th grader taught me super tic-tac-toe.
Is that, I wonder if that's the same as Ultimate. Is this the tic-tac-toe and tic-tac-toe?
Yeah,
Okay.
the tic-tac-toe box with the 9 tic-tac-toe
Yes.
boxes. Yeah.
So
It's probably called Ultimate. I'm hearing in my head, Mom, that's not what it's called.
there's so many different names to stuff like this.
Yeah.
And there's different rules as well. So it's tic-tac-toe within tic-tac-toe. And so what you do, and again, the whole point is whenever you have something, you want to generalize it. And so one way to generalize tic-tac-toe is to play tic-tac-toe in tic-tac-toe. And so we'll play right now, but we won't play seriously. So Stephanie, where would you like to go?
I would like to go in the upper right of the upper right, please.
So you're going to go in the upper right of the upper right. So
Which makes it hard to teach anybody how to play this game.
no, it's fine. So I will explain what goes on. And so the way machine learning works is machine learning would just observe games and try to figure out the rules. The rule is I must go in the same board as indicated by your move. So if you move in the upper left, I have to move in the upper left board next. If you move in the upper middle, I have to. So because she moved in the upper right, I have to go somewhere in the upper right. I will seize the opportunity and take the center. And now that forces Stephanie to go somewhere in the middle.
I'll go in the middle left.
So now she's going to go middle left
of
side.
The middle left side of the middle block.
So over here.
Yes.
Okay. Again, we're not playing seriously. We're not trying to beat each other. We're just trying to give you a sense of the game.
Wait,
Okay.
I'm trying to beat you.
So she
She has
moved
to go to the middle
because I moved in the middle of the square. She now has to go into the middle.
of the whole.
Of the whole.
Okay.
But she
Right.
gets to pick the
But you
spot
can choose
that.
anywhere in issuance. Because she went in the middle of the left column, I now have to go in the middle left column of the big board. So in an act of surprising stupidity, I'm going to seize the center and give her another opportunity.
Oh, I'm gonna go on in the middle, the huge, in the
Yep.
middle of the huge one, I'm gonna go, yeah.
Yeah, I know exactly where Stephanie's going to go. And to illustrate a point, Henry did make sure and Mary did make sure that you have a good instructor. I'm going to continue my fixation on claiming as many centers as possible and take the center there.
All right, oh, I'm gonna get a 3 in a row.
And so Stephanie comes over here, she takes the row. And so now this whole becomes an X. And now you can have different rules for how you proceed from here. The simplest is Stephanie has now won the game. She has 3 in a row somewhere. Another way of looking at it is, well, that's only 3 in a row and 1. You need to have control of 3 small tic-tac-toe boards. Now the question becomes, can people still go in a board that already has something on it? You know, now that you've already taken over the cell, can I go into it if I'm forced to? Sure. And then what if I get 3 in a row on that? Can I override your X? No, well, but this is the whole point, is trying to come up with good rules. And so if I get the top 3, do I now remove your X? And if I get the top 3 and the bottom 3, can I replace this with an O? Or maybe if I get 3 in a row on the top, my O trumps your X's because it was the last one and it changes, you know, so you have some freedom. If one of the cells is completely filled, sometimes people then play, you have a free move and you can go anywhere. So the whole point is to try to take something that you know and make it more interesting. Another way to play tic-tac-toe is to increase the size of the board. What else could you do? And this is related to the tiling problem. How else could you make tic-tac-toe interesting? 3D. What if you played 3D tic-tac-toe? Do you think player 1 has a winning strategy in 3D tic-tac-toe? It's a little bit harder sometimes maybe to draw and visualize what's going on. Where would you like to go? Gut feeling. Middle. Middle of which?
Middle of the middle.
Middle of the middle, right? That seems like the best possibility. There's so many things that are going on. Without loss of generality, can we always adjust things to assume I'm going somewhere in the middle board? You know, can I just like rotate things and whatnot?
Wait, what was the question?
Without loss of generality, can we always assume I'm going in the middle board? Or is maybe the top somewhat different than the middle? You know, in terms of like slices and whatnot. I don't think you can quite assume that I'm going in the middle.
Even like the corner, there's no way to rotate it.
So if you go in the corner, there's no way to rotate it. So the corner is at least different than the middle. We know I don't want to go in any of the middles.
Yeah.
So what we can immediately do is I'm going to just cross out these middles can't work. But going up and down, that also kills those middles and the ones down here. And It should also kill. Okay, I think we've killed everything.
Wouldn't it kill right above and right below too?
But I think if we rotate it, can we look at, say, the 3 down here, the 3 here, and the 3 here as a tic-tac-toe board? And if we do, I can't go in any of the middles, right? And so again, this becomes, how do you present the information in such a way that people can process it? Do those 3 make a 3x3 tic-tac-toe board?
Yeah.
Yeah.
Diagonal, yeah. But why wouldn't you eliminate, like I'm seeing it as like the top one is like the top layer, the middle is like horizontal.
Right.
So why wouldn't you eliminate the middle of the top layer? Like, why isn't that a middle of an X going up and down? Like, why isn't that a green knockout?
So let's give things notation. Level 1, level 2, level 3, and we'll label the squares, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can now give me some notation. So which cells are you talking about?
I'm talking about level 3.
Level 3.
In the middle.
So which one?
5.
5.
Why can't, so 5 is right above X. Right?
Okay.
And is it 5 right below X? and
Yes.
1?
So we should be able to eliminate that by doing the same argument. Yes, absolutely. So I was doing another elimination first, but yes. So we can eliminate. Oops. We can eliminate 5 here, and then we would eliminate 5 down here.
Yes.
And then if we look at the purple ones, that gives me another board as well. So that eliminates, I believe, here and here as middles, and the other middles I think have already been eliminated. And in fact, that would have also given us the 2 ones you just eliminated as well. So there's multiple ways they eliminate. So we can see this is a great example of how math works. You break things down into smaller cases. We understand how 2-dimensional tic-tac-toe works. Now when we pull up to 3 dimensions, we try to reduce to what we already know. So Henry has already warned you I tell inappropriate jokes. I will risk telling this one. My brother is an engineer, so my brother and I are walking down the street, and we see a house on fire, but fortunately there's a fire hydrant in front of the house. Unfortunately, the hose is disconnected. Well, I am a kind, caring, compassionate person. I connect the hose, turn it on, put out the fire. We keep walking down the street, and eventually we see another house that's fine. There's a fire hydrant outside it with the hose connected. I know exactly what to do. As a good mathematician, I always reduce things to a previously solved problem. I disconnect the hose and set the house on fire. I now know what to do, and there's of course no need to actually do anything because I've reduced this to a problem I already know. And I continue walking down as my brother looks at me in disgust. So as mathematicians, we always try to reduce to something we already know. Start with something simple, understand that, and then take something that's more complicated and try to reduce it to something simpler. So now look at how many moves we've eliminated from analyzing for tic-tac-toe. And then we can start to think, well, what if we start going in different places? Well, I think there was a comment of, let's look at the upper left corner of the top level, so 1 of L3. Now, a good strategy for X when they're trying to win is you want to have 2 different ways of getting 3 in a row at the same time, because I can't block both of them. So you always want to be moving me in a certain direction. We saw that before. So when we were looking at the game earlier, X went here, O was stupid and went here. X went here, threatening like this, forcing O to go here, and then X came in here, threatening to go this way and this way. And O was just dead. So what you want is you want to set up a string of moves where if you have 3 in a row, that forces me to stop you immediately. That means you know where my next move is going to be. That makes the analysis much easier. You don't have to analyze every possible game. The goal is to get onto a path where you can predict what's going on. Where would you like to go as X now that I've gone in the upper left corner? Where do you think might be a good square to go? So we'll call that x1, we'll call that O2. I have a thought of where I would go as.
The center on L3.
So let's go on the center of L3. I was actually thinking of center of L3 as well. It's okay if you say something that's not right. What's nice is if you go above the center of L3, I know where I have to go next as O. O is forced to go down here. And now you have a somewhat free move. So is there a place you can go that's threatening 3 in a row 2 different ways? I think there's several. So can somebody give me one place? And again, this is where it would be much easier to have something physical,
Yes.
right?
Rubik's Cube.
Rubik's
One
Cube.
of those small, with like bottom 9.
Bottom, so L1, you want to do number 9. So, oops, my X is red.
Or 7.
Could you?
So if X goes here, then it's threatening 3 in a row. Wait, no, because the O in L3-1 is blocking 3 in a row coming up like that.
What about L3, 3?
L3, which one?
L3, number 3.
So if we go over here, I can get, this is threatening to come in over here for 3 in a row, and it's threatening over there to get 3 in a row.
Yeah.
So that would work. I think another place that would have worked is if we'd gone over here, that's also threatening 3 in a row. So there's many different ways that work. So when you moved into the center of L3, that gave me the center of L1 in response, but that was fine. That put you in path. This is not a complete proof that player 1 can win 3-dimensional tic-tac-toe, but this starts the analysis. Did any of you ever teach programming? So if you're teaching programming to students, tic-tac-toe is one of the best games to have the students write a computer program. The simplest, mindless computer is it just randomly chooses from the squares that are legal. The next level is the computer looks to see, is there 3 in a row that it can get? And if so, it does that. The next is to look to see, are you about to get 3 in a row? And blocks that. And you can make computer programs of different levels of difficulty without too much trouble. So this is, a nice game to analyze. Let's do a few more tic-tac-toe variants that are fun. So there is bidding tic-tac-toe. Anybody heard of bidding tic-tac-toe? So the way bidding tic-tac-toe works is we each start off with $1,000. And we bid for the right to move. And there's 2 ways you can play. Whoever wins the bid gets to move and gives the money to the loser, or the money goes to the bank. I like to give the money to the loser. There's 2 ways to handle what happens if you both bid the same amount. One way is like basketball, you have the arrow, the possession arrow. And then you alternate. I don't like the possession arrow because that means there's now a difference between player 1 and player 2. What I like to do is if there's a tie, if there's an exact equal bidding, then you have to bid again. What that means is you might get into a situation where the game just stalemates because nobody is willing to, just like in chess, if there's a 3-fold repetition of board position in chess, the game is a stalemate. So let's play bidding tic-tac-toe. Whoever bids most gives their money to the loser. And I will be honorable and I will not lie about what my bid is. Okay, I'm not going to try hard. How much would you like to bid as a class for the opening move?
Is the goal to eventually get?
The goal is to get 3 in a row. It doesn't matter how much money you have. The goal is to get 3 in a row.
When does this game end? When there's a player on 0?
Nope, it ends when there is 3 in a row on the board or no moves are left. Or everybody keeps bidding the same. So how much would you like to bid for the first move? I know how much I'm going to bid.
500? All of it.
So if you bet all of it,
You can't go again.
you can't go again.
So the maximum amount you have is $1,000.
Correct.
So you can
But
only.
whatever you bid, I get. So if you bid 500, I get 500, and I have $1,500 to your 500.
So you don't
Oh,
have
so you
100?
added it.
Oh, so you'll bet 100. So I'm gonna just accept that, and just so that we don't spend all day on this, you bid 100. I'm gonna overbid and I'm gonna bid $400. So I get the opening move. I'm now down to 600, and you have 1,400. Yes. How much would you like to bid for your next move?
300?
Okay, I heard 300. I'm gonna bid 500. I really want to move. All right, does everybody see how it's played?
Yeah, sorry, I missed the part about you bid for your move.
You bid for your move. So this was meant to just illustrate what's going on. What's the technical description of my state right now?
Cash poor.
Cash poor. I was just talking with my niece earlier today about certain words. If you know what foobar is, that's a really good description of where I'm. Doesn't look like I'm doing well if you look at the board.
Yeah.
Yes, but if you look at the resources, I only have $100 left. You've got 1,900.
So we have to
So
do
you
more than
bid
100, so you don't give them-
$101.
Right, but if you do 101, I'm going to do some really tough math.
You bid 200.
So bid 200 just to make it easy for me, right? So I appreciate you doing 200. So now I have $300 and you have 1,700. Where would you like to go? Yeah, definitely go there to just block me. Now let's bid again. How much do you think I'm going to bid? I'll probably bid all of it.
You're gonna lose no matter what.
But how much did you bid? 400, just to make it nice. I mean, I really do appreciate this. So you're now down to 1,300. Where would you like to go? And there's really only two bad moves. Upper, top right. Yeah. So many good moves for you.
Sorry, just to play dumb.
Yep.
What's the two bad moves there?
The two bad moves would be if you'd gone either here or here. Because that wouldn't be setting you up for 3 in a row. Those would be wasted moves.
Got it. Okay. That's what I thought.
Yep. And now how much do you bid?
800.
You could bid 800. Or you could really, really stump it to me and bid everything so that I'll feel great because I've got all the money. And you go over here and you win. So this is bidding tic-tac-toe. I bid too much for the first two moves. And so I put myself into what looked like a great state, but you have to consider what my resources were. How do you analyze a game like this? One of my friends actually analyzed this and came up with what is the correct strategy. Anybody play golf here?
Sometimes.
Okay. When you play another golfer for the first time, what's the first question you ask them?
Choose your hand.
What's your handicap? So what's nice about this is we can do a handicap. Maybe I start off with 1,000 and the other person maybe starts off with 1,500. So if you're playing with somebody who doesn't have as much experience, you could actually give them a little bit more money. When I was in high school, I volunteered and I was with kindergartners and they decided they wanted the kindergartners to learn how to program. And so they had absolutely no conception of just how big was the screen when they were doing graphics. 1,000, it's not 1,000. And so, you know, young kids are not going to have the same understanding of the size of numbers. Give them a little bit more money so that they can afford to make some mistakes. And so you can try to analyze a game like this. How would you come up with strategies? And then for the older kids, you can have the following. How much is too much to bid for the first two moves? What's the danger if you bid too much for the first two moves?
You don't have the opportunity for a return.
So what's in particular dangerous?
You lose it, sure.
Well, so I mean, I can afford to lose one move to you, but after the first two moves, I had $100, you had 1,900. What were you able to do? I got moves 1 and 2. You got moves 3, 4, and 5. If you can get 3 moves in a row after the first 2 moves, I'm dead. So I can't bid so much that you can get the next 3 moves. So as a simple result. You can ask older kids, how much is too much to bid for the first two moves? What is simpler than asking how much is too much to bid for the first two moves?
Should do it.
No, simpler question than too much for the first two moves is one move. How much is too much to bid for the first move? Right?
Is the next level of this not doing multiples of 100 for the bidding? Is that the next level?
So
I'm not just saying level,
no,
but is
but
that?
that could be that could be an interesting question. Is that not all bids are allowed? And so here, if I can overbid you by $1, then okay, but maybe I can't. And then this now introduces some discreteness problems. And there's a lot of things in mathematics where the discrete maximum is very different than the continuous maximum. And if people are interested, there's a famous problem called the knapsack problem, where if you have continuous stuff to put in your backpack, that's very different than if you have discrete amounts. So this is another example of tic-tac-toe that is interesting. I will show you one more version of tic-tac-toe. There's a difference of opinion between myself and my son as to what we should call it. I like to call it toe-tac-tic. He prefers reverse tic-tac-toe. The goal is to force other person to get 3 in a row. Has anybody ever played this game before? So now all of a sudden you have a game that you can play with kindergartners that's related to something they know. And all of you are starting fresh. We don't know how to play this. So I have deliberately not analyzed this. Do you think going first is an advantage or a disadvantage? Okay, why disadvantage?
There's so many ways you can win.
There's so many ways you could win that if you go first, you're putting an extra one of your pieces on the board. That could be bad. Give me a reason why going first could be an advantage.
To go or you can kind of decide what path they're going.
Right, you might be trying to push the other person to a given path. Which do you think is the stronger factor? Do you think it's worse to have that extra square that's yours versus the small benefit of maybe pushing them in a certain way? And so I'm willing to play reverse tic-tac-toe right now just for fun. I'm not going to play, it's like speed, quick, reverse tic-tac-toe, play quickly. Do you want to go first or second class? Second, okay, yeah. So I would assume that, yeah, second is probably better. I think I know where I would like to go. Who thinks they know where I want to go?
Not the middle.
Not the center, not the center.
The corner, the side middle.
I think one of the side middles. So if you look over here, this middle can be involved in 2 tic-tac-toes, 2 3 in a rows, right? Over here, a corner can be involved in 3. This is not a proof. And that's 5. So again, gut feeling, this is probably the best thing for me. Where would you like to go quickly as a response? I'm sorry?
Just kind of corner to it, up and to the right or something.
So all the way up here?
On the middle of the one down.
One down.
Symmetrically, the one on top of the middle is the same probability rate.
All the middles are the same, yes.
Okay.
For my open move, absolutely. So that symmetry argument still works here. So now it's my turn. So pretty sure I don't want to go in one of those squares. I really don't want to go in the middle. I probably don't want to go here if I can avoid it, because that could be trying to push you into 3 in a row. Probably want to stay away from here. And so, I don't know, my gut feeling is maybe one of those 2 squares. And again, I don't really know. I'm not really thinking that much. I do know that you have an O in this row, so I would probably choose to go there. And again, to me, it's the thought process that's important here.
But didn't you just remove a possibility for
Right.
O's in a row?
Right.
I did. I did, and so the question is, that removes the possibility of O getting 3 in a row, but is that better than maybe going over here, which is still giving me more chances for 3 in a row? I don't know which is better. And again, it depends a little bit on, is my goal to win or not to lose? And to me, I would much rather not be embarrassed. As an aside, in many environments, the goal is not to be blamed for things. And so a lot of people don't take initiative because if things go wrong, they're going to be blamed. And if things go right, they don't really get, the phrase is, the tall grass feels the blade first. If you do something that makes you stand out, you have exposed yourself. Where would you like to go now? Bottom left. Yeah, bottom left sounds pretty. So over here. All right, so what's good about that is you now block me from getting 3 in a row vertically and horizontally. In the first row, I'm sorry, in the first column in the last row. So I'm trying to decide where to go. I might risk going up here. It does unfortunately give me opportunities of getting 3 in a row that way, but I know I can't get anything in the other. So I'll see where you go. Middle top. So that might be a really good move for you. How many moves do you have left? How many moves does O have left? One. Is there any way you can lose? By going there, you guarantee yourself at least a draw, because I have to take 2 out of the last 3 moves. So I know I have to move twice.
You have to go over, right?
I have to, so if I go here, sorry, if I go here, oh wait, that should not be O3. 1, 2, 3, 4. This should have been a 5. And this was O6. So if I go over here as the 7th move, I'm threatening to go like that, and you'll definitely let me do that. So I don't even have to finish analyzing. I know that that's bad. If I go down here, I know it's bad. So I know I have to go here. It may still be a bad move, but I know I have to go there. Is there anything you can do to force me to win? No. So no matter what you do, I'm going to at least get a draw. So this is a nice way to analyze, just some of this, reverse tic-tac-toe. And I love taking games that people know and tweaking the rules and asking kids, make your own game. How would you analyze something like this? Does player 1 have a winning strategy? Maybe if player 1 had done things a little bit better, does player 2 have a winning strategy? Does everybody here know at least the basics of how to play chess? There are some interesting variants of chess. There's atomic chess. So in atomic chess, when a piece takes off another piece, it explodes, and anything in an adjacent cell is killed. Unless it's a pawn. Pawns somehow survive. So this is atomic chess. How do you play atomic chess? If you have too many of your anybody ever read Ender's Game? So it's sort of like the doctor device, the molecular, it destroys everything near it. So you might be willing to sacrifice, a queen if there's enough high-ranking pieces near it, including the enemy king. So you have to make sure that nobody can get close. How do you play something like that? Another version of chess which is fun is the goal is to lose all your pieces. And if you lose your king, you continue to play. And the rule is, if you can jump someone, you must jump them. But if there's more than one piece that you can jump, you choose which one you jump. How do you play chess now, where the goal is to lose your pieces? A lot of it is you try to force the other person to taking your pieces. Because if you can do that, you can often narrow down the possibilities. The last one I'll mention is triple check. If you check the opponent's king 3 times, you win. So you might be willing to sacrifice some high-ranking pieces to just get 1 or 2 checks, because once the opponent has been checked twice, that 3rd check wins the game. And so again, it's trying to take things that everybody has seen and come up with tweaks on them that can be fun. There's a lot of great math in all of this, and you're trying to come up with your game theory and whatnot. I'll end with one last game. I do have nice images drawn, but I'll just do it straight. Has anybody heard of the game Chomp? So the way Chomp is played is you choose on a rectangular lattice a certain position, and then you eat everything from that position above and to the right. So if I chose this one over here, I would eat everything above to the right. If on the next turn, the person chose over here, you would eat everything that survives from there to the right. If they had gone over here, you would eat all of that. Does everybody understand how it's played? I haven't told you how you win.
That's what I was gonna ask, what's the object?
So there's only 2 natural objects. What do you think the winning could be? There's 2 possibilities for how you win.
Maybe most circles.
Oh, okay, I had not thought that. Okay. So one is whoever has the most circles.
So yeah,
One is whoever has the most circles. But I was thinking in terms of
the removal.
the removal. So either you're the last person to remove and you win, or you're the last person to remove and you lose. Do you think it should be whoever makes the last move wins or loses? Loses. If whoever makes the last move is the winner, where would you go in your first turn?
Yeah,
Yeah, bottom.
Yeah.
And the game is over, right? So the winning position has to be whoever goes last loses. Otherwise, this game sucks. Yeah. It gives I Love Rectangles a run for its money for worst game ever. I'm going to prove to you that player 1 can always win. And it's a non-constructive proof. Have you ever heard the phrase non-constructive proof? It means I can prove that you can do something without telling you how it is done. If you teach calculus, think the intermediate value theorem. There must be some point in time at which this happens. I don't know which time. Think the mean value theorem. There must be some point in time in which this happens. I can't tell you when. Everybody knows what happened in November of 2024. The election. Imagine I go up to either Harris, Biden, Trump, RFK, and I say, want to let you know, mathematician, I can prove to you that you have a winning strategy to get to 270 electoral votes. What do you think the first question will be that they ask me?
How do I do it? How?
Well, I'm a pure mathematician. This is an existence proof. It's useful to know that there is a winning strategy available to you. And there's a lot of people who are discussing right now, should Biden have dropped out or not? Did Biden have a path to 270? If the answer is no, okay. If the answer is yes, well, what is that? Well, I'm sorry, I'm a theoretical mathematician. I can't actually tell you what the path is. I can just prove that it exists. I'm going to give you a non-constructive proof that there is a winning strategy. And so there are 2 cases. So case 1, player 1 has the winning strategy. Play it. Okay. Case 2. That means player 2 has the winning strategy. So no matter what player 1 does, player 2 has a response that continues them on the path to victory. Because again, everybody agrees that eventually all the dots are eaten. So no matter what player 1 does, player 2 has to have a winning move. So if player one goes here on their first move, player two has to have a winning response that keeps them on the path to victory. I don't know what it is. So for definiteness, let's say it was going over here. Okay. Now it's player one's turn.
Is this for case one?
This is for case two.
Oh, for case.
So for case one, if player one has a winning strategy, they just play it. Imagine we're in a situation where player two has the winning strategy. So player one goes in the upper right corner. No matter what player one does, since player two has the winning strategy, there has to be a move that player two has to keep them on the path to victory. I don't know what that move is, so just for definiteness, I filled in that circle. And now, no matter what player one does, player two is still going to have a winning response. Player one is going to play the 5-year-old reversal trick. I didn't mean to move there. I am doing callback. I want to move here where you moved. I'm going to call that as my opening move. And now we're in the same position we were a moment ago, except we've changed who's moving next. And this is called a parity steal. Player one has just taken the position that we said was a winning position for player two. So if there was a winning strategy for player two, no matter how player one starts, player one can steal that strategy by just moving there. This is a really hard concept. It's a beautiful result that there are things that we can prove happen without knowing how to actually construct it. This is similar to what we did in the beginning with the Fibonacci's repeating. I can prove no matter what modulus you give me, they will repeat. I don't necessarily know where. And if you gave me the specific number, I could actually construct it by just going through and doing the calculation. But I don't have a nice formula as a function of what that modulus is. And there are people who are working on it, and there are some partial results. I can prove here that player one has a winning strategy without knowing what it is. And so if people are interested, there's a lot of other games we can talk about over lunch. I want to stop now because it is 12 o'clock, but just giving you some sense of things to think about. And if there are things you'd like to explore more in the second half of today, absolutely fine. So this is a good place to stop. So let me hit stop on the recording.
Does the